So hello everyone, this is lecture 8 for the special theory of relativity, that is STR. In the last lecture we just introduced the rotational matrix, and we get the idea what is rotational matrix, and means how we convert it, and how we find the different coordinates in the different rotational frames. Okay, so that was just an introduction. Now we will see that how it is related, means what is its importance or why we are doing that. So we are doing that for this, the space time. First of all, let's define what is space time. Space time is a notion in which all the physical events take place. The Lorentz transformation equation says that space coordinates depend upon time coordinates depend upon space coordinates. Means in the previous we studied that the coordinates of a particle in the xyz axis can be given, and we can find the location, but we see in the relativity that the position coordinates also depends upon the time, that where we are measuring, at which time we are measuring, the coordinates will vary accordingly. In the Lorentz transformation we have seen that when we find the t prime, we have to take the x, the difference between the x also. So these the time and the xyz coordinates depend, they are interdependent, means they depend on each other. That's why now if these are xyz axis and there is a time also which depend on these xyz, then we have to take one more axis now. Then we can describe the whole physical events take place, means all the physical events, then it will be possible to define them. That's why we have this fourth dimension, that is the time dimension. So now we're gonna study about the 4D space-time continuum. The Lorentz transformation equation says that space coordinates depend upon time and time coordinate depends upon space coordinate. That is, space and time is not independent of each other. So in place of xyz system, we need four-dimensional word linking space and time together. This is called 4D space-time continuum. In this continuum, three axes are representing uh, space coordinates, while fourth is a function of time. If fourth axis x4 is ICT as the fourth coordinate, it is referred to as Minkowski's four space. So for a general idea, just hear me out what I am saying with the open mind, that how we define the dimension. Just like in the 1D dimension, there is only one vector we needed, and that one vector can define all the position in one dimension. So that is called the basis. If there is one basis, means one basis vector, then it is one dimension. If it is two basis vector, then it is two dimension. Means in xy plane, we can there is two basis vector actually. With the help of them, we can find any location there. In 3D, we have three basis vectors, same as in the four dimension we have four basis vector, which is x, y, z and the time, and the fourth axis is a function of time. So we can take it the four dimension as anything, like it can be a function of time like t square, t cube, ct, anything it can be. So if we take the fourth axis as ict, here I is the iota, c is the speed of light, and t is time. If we take fourth axis as x4 is ict, then we call that coordinate system as Minkowski's four space. Minkowski's four space. Hope it is understood or it is clear to you. Let's move forward. Now we are talking about the Minkowski's four space. Well, one thing I want to clear, that it is not possible to draw this four-dimensional structure if you are confused that how we're gonna draw this, because you are living in a 3D world. So it is not possible to you to imagine this 4D, but it is there. Okay, this four dimension are there. Well, there can be any number of dimensions. If there is more than five basis vector, then it will call the 5D also. If there is, you find any that dimension, you can introduce, means you can observe only three dimension in the real world because it is 3D world. Otherwise there can be any number of dimensions, that is possibility. So now we are just talking about the 4D, and why we need it, because it makes some calculation easy. So how it is making calculation easy, we will see. So let's say this is that 4-dimension space. Here we are just representing the x1 and x4, and the yz are understood that those two axes are also inter orthogonal, or can say all 4 dimension are orthogonal. You can't imagine how they are, you can't design, you can't show here that how they are, but these are all orthogonal. Just understand this. Okay, x1, x2, x3 and x4 all are orthogonal to each other. So just for the convenience, we define only 2 dimension here, and take that in consideration that there are also two axes which are perpendicular. So let's say this is x1, this is x4, which is time axis, this is x1 coordinate axis, and if now we need to find the coordinates or the position of a event in Minkowski space or 4 dimension space, how we can locate it? We will locate it like x1, x2, x3 and the x4. So now we need 4 coordinates to determine any event's position. So that will be this. And in Minkowski's space, or the 4D space, we call this point as world point. Okay, world point. Now here is this definition. Any event in the Minkowski's space is represented by a point, that is world point. The position of the particle at different times can also be represented as a sequence of events in Minkowski space. Now see, here we define that like if one event is happening, we can define that it is x1, x2, x3, x4. This event is happening here in the 4D space. But how we gonna represent if particle is moving? Particle is moving. How are we gonna represent this? So if something is moving, we can define its positions as events. Means now this event is happening here, this event is now happening here, means this particle is moving here. Okay, so in 4D world we can show that movement as the sequence of events, and if we define in 1D motion, then that motion in the Minkowski space can be represented by a straight line, because the one after the one event is happening or the position is changing with time. So the position of the particle at different times can also be represented as a sequence of events in Minkowski space. Now sequence of events may be connected by a line, and it is called the world line. Just what I already told you, that we can represent that 1D motion, or it's just not 1D, it's like something is moving in the free world, then it's only moving in the one direction na? So that's how we can show this. So that line which came in the Minkowski space, which will be representing the motion of the particle, we call that line as world line. World line. Like, see, here we are representing the motion of a particle, okay, in just one direction. Okay, so this motion can be represented by this line, and this theta will be dependent on the velocity at which it is moving. So this is we gonna study that how it is dependent, how it is. So this is it. This will make us make it very easy to determine any frames, any inertial frames, or the transformation one frame to another frame, all in a single 4D space. Means we just need to rotate the axis, and we will be able to change the frame. Means as in the previous we studied that there is this S frame and this S prime frame, and there can be third frame also. So all these frame can be just represented here by rotation of this rotation of these 4D matrix or the 4D space. Okay, so we will study that how it will be. Okay, so here if this is point, the world point, this is world point, and this line is world line. So here x4 coordinate is ICT, and there is XYZ, and here origin is 0 0 0. Now if we need to find this length, the length will be just like we find in the coordinate system, this minus this square. So it will be x minus 0 square, y minus 0 square, z minus 0 square, ICT minus 0 square. That will give us x square plus y square plus z square minus c square t square. I square will give us minus 1. So s square will be this. Now we already proved that this is invariant in any space. Okay, this is invariant. We already proved in the previous lecture So now we see that this is length. If there is this s prime frame, then this length will also be remain same. In another frame, this will remain same. Okay, so now we thought, or the Minkowski at that time thought, that if this length is gonna be fixed in the different frames, then we can use this type of structure or this type of system to represent any number of frames or any frame which is moving at whatever velocity it is. So we can use this, because this length will remain same. If we rotate this frame will be like this, then this length will remain same, this length will remain same. So we found this length as our bridge from 3D to 4D. Now let's see, if one moves from one inertial frame to another inertial frame in Minkowski space, then position vector remains invariant, as I already told you. Now, how to represent this new inertial frame in the Minkowski space? Now we only need to find that how, if there is this s prime frame, how we can represent that s prime frame in this Minkowski space, because that's our only motive. Okay, and in the last we will verify them with the Lorentz transformation equations, that if that frame we drawed in the Minkowski space verify with the Lorentz transform equation, then we will be able to say that yes, we can solve these different frames in this space. So how to represent this new inertial frame in the Minkowski's frame? Let there is this s prime frame, then the space coordinates will be this in the 4D space, and s prime equal to s, because this quantity is same in s. Okay, so we also can see here also them, like this is particle, this is length, and if this frame is moved, rotated, now this length is still the same. Well, now this is the s prime frame, na? So this length is same in s prime also. Now how we gonna take this advantage to find these coordinates? I already told you this rotational matrix. If the theta angle, this system is rotated by theta angle, then we can find the x1 prime, x4 prime with the help of this. And how we came to this result, I already told you in the previous lecture. And also we can find the previous coordinates after before rotation with the help of this, if you know the current coordinates. Okay, so we will use these equations. Now these are just x1, x4. Now we have to talk about all the 4 coordinates. Okay, so this was the consideration actually, that in this frame we gonna take these two axes only. Other 2 axes will remain at their position, they will not be changed, they will be fixed actually, they will be fixed, and the frame will rotate on these 2 axes only. So if there is something x2 axis somewhere and x3 axis somewhere, then they will remain just fixed, and this will rotate. Now you are just questioning that how 2 axes are there and how they are fixed. So don't worry about that, just about them, because you can't draw, or you can't really imagine in this 3D world about that. Just consider it in your mind that there are 2 dimensions which are perpendicular to these, and all 4 are perpendicular to each other. Okay, so these 2 dimensions are fixed at their position, and this x1, x4 are rotating. Just keep it this in your mind. Now if that is the case, then we can define the equation like this. From here we know that x1 prime is cos theta x1 sin theta x4. So cos theta x1 sin theta x4, and x2 x3 is fixed. In the x1 prime it will be fixed now. So 0 x2 0 x3, this will be the coordinates for x1 prime. For the x2 prime there will be some x2, so for that there is nothing in x1, nothing in x4, and nothing in x3, but at only the x2 axis, that is x2. Okay, same in the x3 prime, there will be that coordinate only in x3, other 3's are 0. Okay, because these 2 axes are fixed, that's why they have only their own coordinates, otherwise all are 0. But for the x4 prime, from here we can find x4 prime will be minus sin theta x1 cos theta x4. So minus sin theta x1 cos theta x4, other 2's are 0. So now we get this transformation x1 prime, x2 prime, x3 prime, x4 prime in terms of x1, x2, x3, x4. We can write all these four equations in the form of matrix. That is x1 prime, x2 prime, x3 prime, x4 prime will be this. Now, okay, we find the expressions. Means we find the expressions for the in S prime frame. We can locate all the coordinates with the help of initial coordinates. Now we need to verify that it is right. It is right. How are we gonna verify that it is right or it is possible? And definitely it's very easy if we are able to represent this like this, the S prime frame. But we didn't verified it. How are we gonna verify it? Because how are we gonna verify it? So the only solution is for the transformation from one frame to another, we use Lorentz transformation equations. If these all system verify the Lorentz transformation equation or they came equivalent, only then we will say that these things we did are right. So let's see. Now we have these two frames. The general case we all know that there is this S frame, there is this S prime frame, and this S prime frame is moving with velocity v. Okay, this is, we know very well what is this. Now consider the motion of O prime. This frame is moving. Origin of S prime frame, that is O prime. Now if we want to find the coordinates of x1, then how are we gonna write them? We're gonna write them as this. We need to verify these equations, na? So according to that Minkowski space, we're gonna write these x1 as cos theta x1 prime minus sin theta x4 prime, and x4 as sin theta x1 prime plus cos theta x4 prime. Okay. So we need to verify these equations. According to Minkowski space, x1 x4 should be like this. Okay. Let's now what is x1 prime? What is x1 prime? X1 prime is the observation of x in this frame, and this whole frame is moving, so x1 prime is not changing. It is just at the origin, so particle is at origin. Okay, so if this whole frame is moving, then this coordinates is not changing in this frame. This will be 0. It is changing only in this frame. So if it is moving, then it is x and x plus v delta t this. But the particle here in this frame is not changing coordinates, so x1 prime will be 0. Put it, we get this. So x1, now from here divide this equation by this equation, we will get tan theta equal to minus x1 by x4. X1 by x4, this will cancel out. Sin theta by cos theta will give us tan theta, and minus sun will be this. So tan theta equal to minus x1 x4. Now what is x1? X1 is coordinates of this particle in this frame. So this will be x. So x1 will be x. And what is x4? X4 will remain same. This if it is at the time t, then this is representing time t. So we can write this as x4 actually. So it is ICT here and ICT here. In this frame, all these frames, this time is remaining same. So we can write it ICT. In this frame it is t, and we are taking in this frame na, x4 is in this frame, so it will be ICT minus x by ICT. Sorry for that, the time is not gonna remain same, it is different with different frames. But now here in the x4 in this frame is ICT. Now what is x? If it is moving with the speed v, then in the time t, this distance will be vt. So x equal to vt by ICT, t will cancel out, multiply I in the numerator and denominator, we will get minus plus and IV by C, that is tan theta. Now we get tan theta, then we know trigonometric equations, we can find the sin theta and cos theta. So make a right triangle, this, and now from the Pythagoras theorem we know that this is square of this plus this square of this, I square will give us minus, so root 1 minus v square by c square is this hypotenuse. Now sin theta will be this I beta IV by C divided by this, and cos theta will be this. Okay. Now see what we are doing here. You can see that we are representing or showing theta related to V by C. Theta is related to V by C, and V is the speed of that moving frame. If that frame is something different frame with different velocity, then theta will change. So theta is proportional to velocity. And what we take this assumption, we are rotating this Minkowski space, only rotating, and on the rotation this theta is changing. So in any frame, any s prime frame, if there is this velocity, then that velocity is related to theta, and with changing theta we can represent that frame. So if it is rotated at this, means we are showing that frame which is moving at particular velocity, and if it is rotating at other theta, that is at different velocity. So just if you are getting this understanding that how these are things are related. Okay, so we get these. Now we have that matrix from which, well, let me explain these expressions also. We know that this is gamma, and this is gamma, and we call V by C as beta. So this equation can be written as 1I beta gamma. Okay, now we need to verify this matrix. This matrix turned out to be this. How? Because we write cos theta as gamma and sin theta is I beta gamma. So sin theta is equal to I beta gamma, cos theta is gamma. So this equation turned out to be this. Now we need to prove that this equation is equivalent to Lorentz transformation. So let's write it. X1 prime equal to gamma x1 I beta gamma x4, other two will be 0. It will be like this. So x1 prime equal to, take the gamma out, and it will give us 1 root 1 minus v square by c square, x1 plus I beta, beta is v by c, x4. Now what is x1? X1 is x. What is x4? X4 is ICT. So it will give us I square, c will cancel out, I square vt. So I square vt here. I square will turn out to be minus, c will cancel out, and it will give us x1 prime or the x prime equal to x minus vt root 1 minus v square by c square. This is our first Lorentz transformation equation. We already see. So it is verifying first Lorentz transformation equation. Okay. Now let's see the second one. X2 prime equal to x2. From here we can get that x2 prime equal to x2. Other 3 will be 0. So this is, and the same we have y prime equal to y in the Lorentz transformation equation. So second transformation equation is verified. For the third, x3, here is this prime, x3 prime equal to x3, and same z prime equal to z. We know that this is third Lorentz transformation equation. Now the fourth one, x4 prime equal to minus I beta gamma x1 plus gamma x4. This. Now we have x4 prime as ICT prime. In this frame the time will be given by t prime, and IC will remain constant in all the frames. ICT prime will give us, right, beta as v by c. We know that x1 as x, x4 as ICT, and gamma is in down in this. Now from here I will be cancelled out in all that. C, let's divide the whole equation with c. Okay, when you divide the c equation c, then it will turn out to be v by c square. This will be t only, I is already eliminated. So t prime will give us t minus v by c square x divided by root 1 v square by c square. This is our fourth Lorentz transformation equation. So these all four equations are verified with this. Means this matrix actually represent the Lorentz transformation. So now we are proved that yes, we take this Minkowski space in the rotational axis with the in the right way. Means yes, by rotating this frame we can represent any inertial frame with moving at whatever velocity it is. That velocity will give us different thetas, and that different theta we will have this different Minkowski space, this 4-dimensional space. So to understand it better, go through this lecture again, okay, and clear your understanding. If you have still any doubt, you can put in the comment section. I will try to resolve that. So what this concludes? So we can conclude that this rotational matrix is equivalent to Lorentz transformation equation. As Lorentz transformation equation transforms from one inertial frame to other, so rotation in Minkowski space is actually representing transformation from one inertial frame to another. The thing I already told you. In this way, we can represent different inertial frames in Minkowski's frame just by rotation of x1 and x4 axes by keeping x2 and x3. These all are orthogonal axes which are fixed. To fix these x2, x3. This is frame. We can represent any inertial frame in this frame. Here theta is velocity dependent, as I already told you. There will be different thetas for different velocities of the frames. Okay, sine theta given by this, cos theta given by this, and we know that what is tan theta. Tan theta will give us IV by C. Yes. So I hope it is clear to you that how things are going here. So just get a good understanding of this, then we will start the next lecture. It's just ending. We just get a very good view of Minkowski space in the next lecture. Then we will discuss some questions and we will end the STR. Okay, thank you. Just share this lecture with others also who should see this, and just thank you.